My name is Dr. Shobhusha Chishen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bouquet is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you'll be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we'll be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Okay, welcome back to my class on quantum mechanics 2. Okay, it's, as I mentioned, it's a part of your Physics 2 course. In Physics 2 course, you are learning a number of modern topics, and I often mention most of the topics are kept in line with the requirement of your own engineering domain. We have kept the latest computation called quantum computation, which will be an application of this first chapter you are now going through, that is quantum mechanics 2. Now, actually, most of the things that I will be covering in these courses are all the application of quantum ideas. So you'll be learning about the semiconductor devices, storage devices, display devices. Everywhere
you have to explain your something that you are learning from these elementary classes on quantum mechanics. Some techniques I will teach you. Those techniques need to be applied. You will be solving problems of quantum mechanics. Those problem solution, those results will be needed in your introduction in your nano materials class, because nanomaterials are the latest material. Okay, they have in every sectors of our life now, starting from electronics to daily livelihood, everywhere. Now uh, all the materials are now switching over to nanomaterials. Okay, so what are nanomaterials, how to treat that matter, how to describe the electron flow inside a nanomaterial, these are all quantum ideas. So knowing the basic techniques of quantum mechanics is therefore very essential if you have to learn all those future chapters or future topics. So basically, in my courses now, I am now developing that foundation. ABCDs of quantum mechanics, how to tackle a mechanics problem, mechanics of microscopic world with these quantum ideas. That is something I am offering to you. I will be solving a problem of a diode, junction diode. You will notice. Uh, if you use quantum ideas, you will see it is so beautiful. Okay, same diode will be showing some other function. So one of the application of a normal diode is a switch, which is used in the design of logic gates, that is switching action, off on, high low, 0 on action. Now if I use quantum ideas, I will tell you that the same junction, pn junction, will be acting as an oscillator. So this something is waiting for you, so let us explore that. And I told you that in order to do so, to learn all these things, basically what you have to do, you have to remember a few basic things in mind. Okay, so this is my basic introduction, which you I've been presenting every day. And now something that I've been telling you almost every day, that four things can happen in nature. That a matters can be matter-like, collision. Wave can be wave-like, superposition. Wave can be matter-like, the photon concept. Now, if you look back here, all your earlier courses, material nature of matter, Newton has taught you. So I've got no business. Wave nature of a wave, you have learned in interference courses. Superposition is the best exhibition of wave nature, I often tell. And particle nature of a wave, that is photon concept, that you also know. So I don't have to tell you that. What I have to tell you is the concept that is generated out of the Broglie, that a matter could be wave-like. Okay, that is something new. And in this quantum mechanics course, you only focus on that issue. So the objective is very clear. So what I tried to highlight in the past few days, actually, okay, that means if I've got an electron moving, because my object is always electron in this class, where we talk about microscopic particles, in say I'm defining electron with mass, velocity, momentum. So that means I'm taking it like a matter. So it is a possibility of colliding with another electron. Now, if how two electrons collide, that is not my prerogative, because that you know from earlier classical mechanics, which you do not know if the same electron follows the idea of the Broglie. It is showing the wavy nature. It is no more the material nature of the, okay, we are interested about its wavy property. The wave nature of the matter electron, that is the focal point. And this is not a story, it has been proved by Davisson and Germer. So basically this wave, what is this wave? These are the waves of electron. Okay, this is something known pictured to you. And I told you these waves are not electron. These are the probability of finding the electron. So the wave that I talk in a quantum mechanics class is not like usual wave like light and sound. It's a mathematical wave. It's a wave of probabilities. Okay, sound wave is a vibration of material particle. Like electron in the AC signal is a vibration of electric field. Alternating magnetic field is a vibration of magnetic field, and electromagnetic wave, the light waves are the vibration of both electric and magnetic field. So something physically meaningful entities vary to make the waves, Now to make this new kind of wave, the variable is the mathematical entity, the probability. Sense is very usual, common sense, that I have got suppose I've got an electron moving, as you can see in the picture. My problem, the way I see a big object, a car, I cannot see the electron in that way. So I have to take chance to find out the electron. Chances will vary, as you can see in this picture. Okay, chances will vary. So if I look at a given point, at that particular point, the chance of finding the electron is varying every time. So any variation, any fluctuation makes a wave. So it's a wave of chances or wave of probabilities. But I told you several times that this variation may be both plus and minus, but probability cannot be negative. So that variable we define as a function psi, and psi square gives you the mod psi square gives you the probability of finding the particle. So the total probability makes it 1. So therefore, anything we do in quantum mechanics, suppose arbitrarily electrons are moving in an atomic system. So your primary job, if you have to, it's a mechanics problem at the end of the day. And any mechanics begins by answering two WH questions. That is where and when. That is where the object is at a given point of time. Now to answer this question, where the object is at a given point of time, I need to know mod psi square, its wave function's modulus square. Now that I can only answer if I know psi. Question is that who is going to give me psi? Answer, you was told to in your previous class. Psi is a function. Suppose I've got a moving electron. I want to get its psi. Who knows the psi value of psi? Schrodinger knows the value of psi. Then I presented it in this way. Psi is a function of mathematics. So you have to solve a differential equation, popularly known as Schrodinger equation, to get the function psi. Because if you look at the screen, it's a differential equation. It's a first, second order, first degree partial differential equation. Why partial? Because psi is a two variable function, space and time. So where V is the potential energy term, the meaning of V I told you, the V will be present in a problem if some force is there. V will be absent in a problem if no force is there. That is a case of free particle or free body. So from problem to problem, our main concern will be solving the problem, that is the change in V. We'll do that. We'll solve actual problem there in those classes. We'll come to know. But I have actually raised one issue in the previous class, that if you look at the problem, look at this equation, solution of the differential equation, is not the easiest job in the world. Nobody likes to solve a mathematical equation. Mathematical hazards are there. So basically, if you have to stay in a quantum mechanics course, you can understand, first thing you have to know psi. Psi is the matter. If you know psi, you can do many more things. We'll tell them what you can do. And to get psi, your first job is to solve this differential equation. So you can realize that if you have to stay in quantum mechanics course, you have to deal with Schrodinger first. So Schrodinger equation is regarded as the basic equation or starting point of quantum world. That means if you have got an electron in motion, to describe the problem, you have to solve Schrodinger equation. Okay, you have to solve. There is no other option, which is the second order first degree differential equation. Now, if you get a similarity with the classical mechanics, where suppose I've got a train moving, you can see some trains are moving, beautiful motions are shown in the picture. Okay, trains are moving or a man is walking. Now, these are all classical mechanics problem because I am talking about large objects. Okay, you see, the man is walking. These are all classical physics problem. Now, for this classical physics problem, if you have to describe the motion, Newton is there to help me. And if you look at this is a variety of the problem I presented. Okay, a body can move, it can fluctuate, it can oscillate, it may be under some force, anything can happen, and everywhere Newton is very good. There are so many problems. Okay, variety of, you solved hundreds of problems in your earlier life. A pulley motion, somebody under friction. What happened from problem to problem? Suppose a train is moving, that is one problem. Somebody oscillating, that is another problem. Somebody under friction, that is another problem. Somebody under rotation, that is another problem. But the common factor, everywhere the nature of the force is changing. So, and you calculate force and solve a problem, that means you are thinking in the line of Newton. And so that means each time you solve a problem, you solve this differential equation. And I tell you, this equation is also a second order first degree differential equation. So, and this is, so any classical physics problem you solve with this Newtonian equation, and you are solving essentially from mathematical point of view a second order first degree differential equation. Similarly, if you are dealing with a quantum mechanics problem, which is also a problem of motion like electronic journey, then Newton is helpless. You have to follow the idea of Schrodinger, okay, which is also a second order first degree partial differential equation. So mathematically, with the point of view of mathematics, there is no difference. Everywhere you solve a second order first degree partial differential equation. But major change is in the physics perspective. In a classical mechanics problem, Newton is very good because you can see the matter, you can measure the force, source, etc., everything. But in a quantum mechanics problem, your basic physics is different. You cannot see the matter. You are doing mathematics to find out the matter. You are defining a function to describe the matter. You are taking the square modulus of the function to get the matter. So that psi, that is the function psi, and that is psi you are trying to extract by solving this equation. After knowing psi, you can develop the entire mechanics as you learned in Newtonian ideas. Okay, so you can do that. You have got that advantage. But basically, if you have to do anything in classical physics, you have got Newton to help you. So you say classical mechanics begins with Newtonian idea, which is a second order first degree equation, and Schrodinger equation is a basic equation of the quantum mechanics. So if you have to live in quantum mechanics, you have to deal with Schrodinger. So quantum mechanics begins with Schrodinger equation, second order first degree equation. Classical mechanics begins with also second order first degree equation, which is called Newtonian equation. So structurally, both of them are same. So mathematical point of view, both of them are same. But you can one thing you should realize. You see Newton's equation, which is shown here. You see nobody of you have derived this equation because it is a law of Newton, second law. So it can't be derived. Similarly, in quantum mechanics also, if you have to solve any quantum mechanics problem, you have to use Schrodinger equation. Mind it, this equation itself cannot be derived. It is the beginning of classic quantum world. So in your book, you will notice there is a long deduction done. Don't learn it. Obviously, it cannot come from sky. Some Schrodinger has to get it, but from a different aspect, from the wave equation, etc., etc. So you will begin. We'll consider this is my beginning equation, and we'll solve 100, just like you use Newton's formula, Newtonian equation to solve hundreds of classical physics problems. So here also we'll be solving 3 problems only with the help of this equation of Schrodinger. Okay. So now what I did the other day, I tried to convert this equation in an easier form. Okay, and that's for that purpose. Okay, for that purpose, we use the technique of mathematics. Okay, the contribution of V I just discussed. That is called the technique of separation of variable we used. Now, just to make you remember what we did, we define a trial solution e to the power I x kx minus omega t. I is there to represent the wavy nature of the solution, and we divided this into 2 parts. Written psi as a product of 2 functions. One is x dependent function, another was a t dependent function. Next job was very simple, to replace all the psi x d2 psi dx to b psi and del psi del t with the right hand side. Okay, I did it also. So you can see if you do the replacement, your equation takes a form like this. So after that, we divided every term, okay, the psi and phi, psi and f, and we get an equation whose one side was depending on x, the other side was depending on t. You can see here, I told you this is very similar to this analogous problem of mathematics, where one side depends on x, other side depends on t. So it is only possible if x and t are dependent on each other, but in our problem, x and t are independent variables, space and time. Okay, time is actually the 4th coordinate according to relativity, you should know. So basically it is only possible, even if x and t are independent of each other, but they are already equal, it is only possible if they both sides produces some constant quantity, as it is shown by this example. Okay, it is an arbitrary example. You can see if both sides are producing 10, even if x and t are independent. So what is the speciality of 10? It's a constant. So if both sides are producing some constant quantity, then and only then it is possible to be, they should be equal. So this is the solution of the time part, which anybody can solve at your age. But our main concern will be the space part. So this equation in space part, as I did it by hand also. If you can check my video, that is, this equation is called the time independent Schrodinger equation. And when we'll be solving actual problem, our main concern will be on this time independent equation. Why it is time independent? Because there is nothing like time. Okay, and in problem to problem, V is going to vary. Now, so at the top you can see this is a time dependent Schrodinger equation, and at the bottom we end up with the time independent Schrodinger equation, and it's a full 5 marks question of examination to convert that, write down time dependent equation, convert into independent form. That is something we answered. Now the question is that suppose I get a psi by taking all the pain of mathematics, I have calculated psi. Now what to do with psi? So far, you know, if I take mod psi square, I can know where the object is. But question is that what else I can do with psi? Now to get this idea, because you see, to you at the end of the day, psi is just a function of mathematics, sine function, cos function, e to the power function, whatever it may be. But only telling a function is not going to serve our purpose, because we are doing the solution of some problems of quantum mechanics. So what else psi can do? What we can do with psi, or what is the, because you have to know that you only know psi is a function. It is just like any mathematical function. Unless and until you put physics into it, then entire calculation, entire discussion is meaningless. So what shall I do now? I'll ask Schrodinger to take a bit of rest. Okay, we'll be solving this actual problem with Schrodinger equation later on. Before that, let us develop some more ideas so that we can interpret psi properly. Now, in order to do so, I'll take a very simple example. The example is this much. You see the example. I give you some mechanics problem, okay? In the elementary part of my video also I mentioned some mechanics problem, okay? I have shown you some balls, if you could notice. You see, these are all mechanics problem. One is the vibration of a spring and another is a rotational problem. My question to you is that what do you mean by the mechanics of this object? At one show, it appears that a spring is moving up and down, so it's a vertical motion. and a ball is rotating around. I put some more mechanics problem in front of you. Okay, just like that. You see the spring is moving up and down and some curves are generated, or the pendulum is moving. These are all mechanics problem, and you see I am plotting that. Now question is there, how do you know the balls are moving, the pendulums are moving, springs are vibrating? Answer, you know that, you see answer is in the plot. What I plotted there, can anybody interpret what I plotted? I plotted the change in position of those the blocks against time. So what I am trying to learn, we are trying to see how the position of the object is changing with time, and that is the fundamental question of mechanics. If position of an object changes with time, then you say it is in motion. It may be the motion of a spring, or it may be the motion of a pendulum. You see, I request you to see the motion of the pendulums carefully. There is a red pendulum and there is a green pendulum. You see, if you look at that both the pendulum, you will notice. If you look at both the pendulum, you please see the two different curves are there, because red pendulum is moving almost smoothly and green pendulum motion is not that smooth. It is somewhat damped. So how do you know these two are different motion? These two are, because their displacements are different. Displacements are different means with time they are actually occupying different amount of position. Okay. So fundamentally, to know whether anybody is moving or not, the first question you need to answer is position of the object at a given time. And just by looking at that, we can actually differentiate the motion. You see, two springs are moving, black and blue. You see, well, the blue one is, if you look at the blocks moving under spring, the blue one is under damping. Okay, you see, the displacement is different, amplitudes are different. And so after some time, it is getting decaying, the blue one, and the black one is happening so smoothly, so happily it is taking place. So it is generating a particular sinusoidal wave against the time. So this tells you a lesson. If I just kept these two examples, it's for the pendulum also. Red one is moving so smoothly, and green one, you see, it is saving messing. It has made a mess in between. Okay, there is almost no displacement. So how do you know they are happening separately? Answer is very simple. That they are getting displaced differently with time. Their positions are getting different. So now who told you their positions are different? You yourself told. So basically, if you look at the mechanism taking place, the motion is taking place. So the object is the pendulum or the spring or the bob connected with spring. But observer is you, and your job is to do some measurement. So what do you measure? You measure the positions of the object at various time, and that is a message. That if you have to describe any motion, it may be the motion of a spring, it may be the motion of a pendulum, or it may be the motion of a train, bus, tram, whatever it may be, or it may be the motion of an electron inside an atom. Fundamentally, to know whether the object is moving or not, your job as an observer is to note, is to do some measurement. What do you measure? Is the position of the object at a given time or after some time. Now you see, I put some more examples in front of you. You see the motion of the train. If I now say, suppose the train is now here at this particular time noted by your clock, the train is here. After 1 hour, where did it go? So now I am asking you to be predictive. Now, if you have to, one option is there, you run with the train for 1 hour. It is not possible. Okay, not physically acceptable. You have to do something else to do the prediction. Okay, what is that something else? Or is a man is walking, where he will reach after 1 hour. You have to do some prediction, and you know from classical physics, you need some more data apart from position and time. It's momentum, it's force, velocity, okay, acceleration, all these things are going to give you. Now another thing, so that means to describe the motion of an object, only position is not good enough. That will tell whether it is moving or not. But to describe it fully, that where it will reach after some time, you need more data, like velocity, like acceleration, all these things, okay. And another option, you see, this is again few beautiful examples are there. You see what is happening with the trains, okay. You see what they are doing. You see it's collapsing. You see. So basically, these are all mechanics problem. At the end of the day, it may collide, it may collapse. So for a collision, the moment I talk about collision, few more parameters are coming into business. You see the right hand side train, it is colliding. So for collision to describe, see the examples very carefully. That will give you all the lessons. You see train is falling down, train is coming and colliding. So whenever you are describing collision, some more physical parameter coming into business. They are like energy, they are like kinetic energy means, mechanical energy means kinetic energy, potential energy. You know, for every collision, momentum is conserved. So momentum is another important parameter. For elastic collision, energy is conserved, kinetic energy, potential energy. So what I am trying to tell you, an object, a train, can do many things in the journey. Whether it is moving or not, that you get to know that you have to measure its position at various times. Where it will reach after some time, you need more data, like its velocity, acceleration, momentum, etc. And if it collides, you need more data, like kinetic energy, potential energy, etc. Now the question is that if I know all these data, I can successfully describe a motion. Some more motions are there. You see somebody is falling down. Again, to describe this motion, I need two bodies are colliding. Okay, to describe this problem, there are so many examples I have given. I need to measure minimum these data. What is the change of position with time? Velocity or momentum, kinetic energy, potential energy, force, all these things will describe the motion completely. So all these things together, what they are doing, they are single motto, their single objective is to describe the motion of an object, dynamics of an object. So these variables together are called dynamical variables. Now the question is that how to measure this variable in classical physics, you know. Suppose pendulum is getting displaced, you have to only put a right scale and a clock to get the displacement. Okay, and if you have plotted also. Now from two difference of position and time, two difference of time, I will get velocity. If I know mass, I will get momentum. Half mv square is kinetic energy. If it is under gravity, mgh is the potential energy. So I don't have to teach you that, you know that. So this is your classical concept. Now the problem is that in my class, we are not happy with train bus. Our main concern is about this problem, electrons. Electron, you see electron is moving. The electron is represented by a function psi. And as electron is moving, you see psi is changing. Okay, and my problem is that electron is moving means it's a mechanics problem. You see so many motions I have shown in front of you. It's a mechanics problem, but my problem is that I cannot see the matter. I have to go for the probability of finding the electron. As you can see, some probability may be high, some probability may be less. This defines the function psi. Okay, probability of electron. So that is, if I know psi, I can get the psi from Schrodinger equation. Psi square will give me the position. But how do I get the other dynamical variable? Like the electron is moving, so it should have some momentum. Electron is moving, it should have some kinetic energy. How do I get it? So that is something we are focusing in the class now. I show you another example. You see 3 electrons are moving, 3 wave packets are moving. Okay, so you see red, green, and blue. So they represent. How do you know there are 3 electrons moving? You can see by the motion. But in actual sense, I don't have that advantage. I cannot see the electron. To me, electron is represented by a function, wave packet. This is called psi. But electron is moving, so it should have some momentum, some kinetic energy. So we are now focusing on how do I get this variable. So we have to adapt a technique for that matter. And the technique is simple. We will now, you see, we have our approach will be like that much. You see, 2 ways we can get any data. First way is that suppose I ask you, what is your, suppose somebody is, suppose I've got this pen in my hand. Okay, to know where the pen is, okay, with respect to a coordinate system, I have to define the origin. I have to determine its position, the separation from the origin to know the position. Now this type of measurement is called a direct measurement. So I don't have the option to ask pen where you are. I cannot ask it. Okay, so I don't have that advantage. But suppose somebody is moving by a train. One train is leaving Kollani station now. Okay, and you have to, it is moving with some velocity, say this much. So you have to predict where it will go after half an hour. So you can use your basic Newtonian ideas to do the prediction. So that is you yourself is calculating that data. This is called direct measurement. Another thing you can do, you can ask somebody in the train after half an hour where you are sitting. He or she will be saying, I am in Barakpur station. This is called indirect approach. So you can do a measurement in 2 ways. Either by asking, do the measurement by yourself, that is called direct measurement. And another is you ask the object himself. Okay. So here in this case, problem is that I cannot see the electron. I cannot do anything by myself. So let us ask electron. Problem is that electron is not a living being. So it will respond to you. Electron to you is a mathematical function psi. So you have to talk with psi in its own language. Because psi is a function, you have to talk with psi in the language of mathematics. Okay. And what are the language of mathematics? Addition, subtraction, multiplication, differentiation, integration, double differentiation. These are the language of mathematics. So if you talk with psi, you have to talk with psi in the language of mathematics. And if you are, suppose you are taking addition, or suppose you are taking differentiation of a function psi. Okay. Now any kind of say del psi del x or something, that in mathematics that is called an operation. So idea is that if you have to talk with psi, I have to use the language of mathematics. It's derivative, it's multiplication, it's subtraction, it's double differentiation, it's integration. So what I have to do, I'm doing some operation on psi. So anything you wish to do, you have to do a corresponding operation. If you have to, that means as if my idea is that psi knows everything. Psi is omnipotent. It's like God. You ask question to psi. Psi, what is the momentum? Psi will give you the answer. Psi, what is the kinetic energy? Psi will give you the answer. Psi, what is the potential energy? Psi will give you the answer. Problem is that psi cannot talk in human voice. So you are talking with psi in its own language. That is the language of mathematics. What is the language of mathematics? Differentiation, integration, etc., etc. Now in mathematics, these are called operators. So the answer is that any information I used to know, you have to do some correct operation on psi with the mathematical operator. And then psi is expected to give you the answer. So everything I wish to know, you see electron is moving, so it should have some velocity, should have some momentum, should have some kinetic energy, but who knows it? Psi knows it. So how do you talk with psi? In the language of operator. So now I have to tell you what is the right operator, correct operator to get the information out of psi. So that is the objective of our class. We want to know how do you do measurement of dynamical variable in quantum mechanics, and herein comes the concept of operator. So operator is there. Operator will talk with psi and give you the information of motion. So now I'll be presenting you in a slightly better way. You can see this table. This is actually representing all the operator according to the whatever you know. The left hand side column is the the list of variables you wish to measure. And first I presented how do you measure them in classical physics, and right hand side I tell you the shift in the quantum concepts. Okay, so let me show you by hand. Okay, so it will be easier for you to understand. Me is this function psi. Okay, so I have to do everything in terms of psi. So how do you do? These are the variables I have to measure. So I'll first tell you how do you measure them in classical physics, then I will switch over to quantum ideas. Classical physics, what you do, these things you know. So you have got some symbols to represent position. For 1D portion, I can see these are like x and t. Momentum is like p, kinetic energy is like t, potential energy is like v. Potential energy depends on the problem, obviously. Hamiltonian is the summation of kinetic and potential energy, we call it h. And you can see this is any other energy. Okay, any other energy I call it. In general, any other energy we call as E. Okay, E is any other energy. So in classical physics, what you did, you have got some formula to help you. So for x and t, I do not use the formula. You directly measure position. Momentum, you have been using this formula, half mass into velocity. Kinetic energy, half m square. Everybody knows it. I don't have to tell you. This can be written as p square by 2m. Potential energy depends on the problem. From gravitational problem, it will be like mgx. For somebody on a Coulombic potential, it will be like 1 by r type of force. Hamiltonian is a summation of these two, p square by 2m plus mgx. And energy will again depends on the problem. This is other than the mechanical energy. Somebody suppose under electric field, then it will take up that form. Okay. So now what would happen? If I now how they change in the quantum mechanical way, you see you are making a jump from classical to quantum world. Okay, classical world means big world to small world. So what you do, you go to the market and get a cap for you. So what you do, for every classical symbol, you put a cap. So it becomes a quantum operator. So x will become x cap and t will become t cap. P will become p cap, okay, t will become t cap. V will become Vx cap, because potential energy is a function of x usually and kinetic energy is a function of velocity, you know. H is a function of H is H cap, V is H cap. Now I request you to remember only two things. That you remember, just like in classical physics, we do not use a formula to get position and time, we directly measure what is the x and t. In quantum mechanics also, we do not use a separate formula. X is x and t is time, unchanged. And you should always remember the operator form of momentum. Momentum operator is basically a differentiation operator. It is del del x. For 1D x problem, it is del del x. If it was moving in y, del del y, like that. Minus h del del x is the formula. Now my request is that you don't have to remember the kinetic energy formula, because classically kinetic energy is p square by 2m. So in operator form, it is p cap square by 2m. So you can calculate this by yourself also. You see, how do I calculate it? Kinetic energy is p cap square by 2m. So p cap square by 2m means p cap by 2m. Everybody knows half m square. So everybody can write down this as p square by 2m. So now p cap is minus h cap del del x. This is also minus I h square del Lx by 2m, minus minus plus h cat square, so it become minus h cat square by 2m. Del Lx on del Lx. What is del Lx on del Lx? Don't make it square, it is a double derivative. Okay, it's an operation. So it is minus h cat square by 2m d2 dx2. You see, anybody can do it. So you don't have to remember it, okay? Only you try to remember the classical formula which everybody knows. Minus h cat square by 2m d2 dx2. And potential energy is a function of x because x does not change, so it remains unchanged. Okay, just like this, it will remain unchanged. So the mantra is that you remember the formula of momentum. So kinetic energy will follow you, and x does not change. Potential energy will also not change. Hamiltonian is a summation of t and v. So just your job is simply add these two. So this is like minus h cat square by 2m. Okay, it is like minus h cat square by 2m. D2 dx2 plus Vx, and energy is different. It is time dependent operator plus x plus del L. Now, so this has been the formula. This has been the formula of getting the corresponding dynamical variable. So what? So these are the operators. These are the differential. You see, getting momentum means you have to do first derivative of psi. Getting kinetic energy means you have to do second derivative of psi. Now, what psi is expected to give? Psi is expected to give you some answer. Now, what answer psi will give when you operate this on the function psi? So those answers, okay, so the response of psi when you are asking question to psi, we'll discuss those answers. How to get it from psi in the next class. Thank you.